Hi everyone, my name is Sherri and today I'll be presenting on field-ready LAMP assays for wildlife pathogen surveillance in Dr. Cameron Sember lab. A little bit about why we chose LAMP and why alphaherpesvirus. So LAMP stands for Loop-mediated Isothermal Amplification. It is a rapid and low-cost DNA detection method and functioning at a constant temperature. If you've known PCR requires a more expensive lab equipment, as well as it does not function at a constant temperature, making LAMP very useful for field work. So since 2015 here, while bird populations in France has been declining due to an alphaherpesvirus infection, our project focuses on developing LAMP assay to detect this virus and in hope of creating a tool that can help monitor infections in wild animal populations. So how does LAMP really work here? LAMP uses 6 primers to amplify a single target DNA at a single constant temperature, making it very highly specific. And also it gives us a visible readouts. So it allows an on-site interpretation without a thermocycler. Our rationale here is that careful primer design combined with empirical optimization would produce assays that are reliable and practical in the remote settings. So this brings me to my hypothesis. My hypothesis here is that LAMP assays can be optimized to detect wildlife pathogens with sensitivity and specificity comparable to qPCR while remaining field deployable. The first objective is to design primers that's targeting the conserved region of the Onychoprion fuscatus alphaherpesvirus and then optimizing this LAMP assays condition through temperature, primers concentration and additives, making sure that it is sensitive and minimizing false positive. And then finally, validating my performance versus qPCR using low resource readouts like CyberSafe dye with an LED transilluminator or a heat block. So my methodology here will give you a bit of an insight on how I conducted my experiment. At the beginning of my project, I began with in silico work. A genomic sequences DNA was analyzed with BLAST and then identifying the conserved target regions. The primers were then designed through NAB LAMP tools and Primer Explorer with my delta G and my GC content for the DNA being checked with previous literature to make sure that it is stable. And then experimentally, I use a synthetic G-block templates for the alphaherpesvirus. After this, my reactions were mixed together with a warm start LAMP reagent as well as CyberSafe dye with 4 replicates per dilution series, and I was able to visualize my amplification through real-time PCR thermocycler, giving me a CQ values telling me how many cycles it actually takes before fluorescence is detected. And then the second way is through an LED transillumination, and this is more equipped for field deployable because the positive reaction will glow under an LED light, and you can visualize it with your eyes without a big thermocycler machine. So what did I get from my results here? In figure A, as we can see, I did a limit of detection test, and we can detect as low as 10 to the negative 10 concentration dilution. This is as few as 4.9 times 10 to the 1 DNA copies. And then for in figure B, we did an optimization strategy where we did a thermal gradient, and we decided that 65 degrees can be our optimum temperature because the higher the temperature will prevent primer dammers and ensure highly specific reactions. So in my visual detection here, I can see the 10 to the negative 10 are still glowing under the LED light, but the NTC, being the non-template control with water, does not glow, ensuring that my primers are very specific, as well as in figure D, the negative control is the Aspergillus niger, and it did not glow. It is only glowing in the positive control, which is the alphaherpesvirus target. So in conclusion here, optimized LAMP are reliable and it gives us a clear visual result, making it very practical for field use. We can use this to expand wildlife surveillance and allowing earlier outbreak detection. As for our next step, we are going to explore RPA as another rapid detection method and colorimetric endpoint detection with pH change for true field deployability. I would like to thank you to the Wild Animal Initiative for funding my project, as well as the NSERC for the Pure Award and the University of Calgary.